Hello, we're going to look at techniques for trying to remove a radical from an integrand using trig substitution. In the upper part of the slide, there are different formats that a radical can come in. You can have the square root of a constant minus a variable term, the sum of a constant term and a variable term, and then because subtraction in opposite order is not equal, you can add in any order, like 3 plus 4 is the same as 4 plus 3, but subtraction, it doesn't quite work that way. If it's a variable term squared minus a constant term squared, then we have the subtraction accounted for in both directions. Specifically, if you find the following formats, the top format, if you see that in your problem, you can sub in x equals a sine theta, and then use the Pythagorean identity 1 minus sine squared theta to rewrite that term with a cosine squared theta. In the case of the addition of two squares, constant plus variable, you can use the substitution x equals a tangent theta. The x's and the a's can be a little bit tricky to find. I'm going to go through some examples to try to help you pick those out, though. In this second case, you're going to want to use 1 plus tangent squared theta equals secant squared theta. Again, all of these are Pythagorean identities, so if you need to refer to those in your Google Drive folder, please do so. And then finally, the third case, where you have a radical with a variable term squared minus a constant term squared, then you'll use x equals a times secant theta to get that set up, and then just a modified Pythagorean identity. So let's jump into our first example. We have the integral of dx over x squared times the square root of 9 minus x squared. This radical has the format of a number minus a variable that fits the top description. And so since it's x squared and 9, we can write that as the square root of 3 squared minus x squared. And from up here, a is 3 and x is x. X stays the same, a is 3, so we'll use the substitution x equals 3 sine theta, x equals a sine theta, so x equals 3 sine theta. If you take the derivative of your substitution, dx is equal to 3 cosine theta d theta. Since x was equal to 3 sine theta, if you square it up, x squared is equal to 9 sine squared theta. Square both sides. Okay, so in the braces in black ink, we're going to replace all these terms in the original integral. This is where you're going to want to take your time and make sure that you do this thoroughly. Once you get everything replaced, a lot of things will fall in place and help you solve this. dx is our numerator. We're going to replace it with 3 cosine theta d theta. X squared is our substitution squared, so that's 9 sine squared theta, a total replacement, 9 sine squared theta, and under the radical, 9 minus x squared is 9 minus 9 sine squared theta. Over here in the red ink, I want to show you how to reduce these radicals once you've made the substitution. The square root, and again, this is just the radical part, but it's in red ink. I copied it here. Factor out a 9. That leaves you 1 minus sine squared theta. Here's where that substitution comes in from your Pythagorean identity. We're going to replace 1 minus sine squared theta with cosine squared theta. And then the square root of 9 cosine squared theta is 3 cosine theta. The 3 cosine theta in the numerator, and then once this radical is reduced to 3 cosine theta, you get a nice cancellation. This 9 out front, I'm going to factor out, so we have 1/9 times the integral Sine squared in the denominator, 1 over sine is cosecant, so 1 over sine squared theta can be rewritten as cosecant squared theta. And then I'm just going to drop d theta down. That's our differential after the substitution. The antiderivative of cosecant squared is negative cotangent. And then that 1/9 is still multiplied in there. Okay, now here's where it gets part 2 of being a little tricky. Is our original substitution was x equals 3 sine theta. Look in the lower right portion. X equals 3 sine theta. If you solve for sine theta, you divide by 3. Draw a right triangle, mark a theta. I usually do theta in the lower corner, but you have a right triangle, mark an angle theta. Sine is opposite over hypotenuse, and that's from the SOHCAHTOA acronym that you learned back in Trig. Opposite over hypotenuse from wherever you marked theta. Opposite over hypotenuse. This third side you find from Pythagorean theorem. Remember, a squared plus b squared equals c squared. So that gives us the square root of 9 minus x squared as the adjacent length. Come back to your problem once you've constructed your right triangle and found all 3 sides. Cotangent is adjacent over opposite. Remember, it's the reciprocal of tangent. Square root of 9 minus x squared over x is how you get cotangent theta back in terms of x. With indefinite integrals, you finish with the same variable you start with. So we've gone from x to theta. Now we're going from theta back to x. Negative 1/9 times our cotangent ratio plus our constant of integration, and we're back in terms of x. If you wanted to clean this up, you can absolutely write negative square root of 9 minus x squared over 9x. Either one of these is fine. This one's totally fine as well. In our second example, we're going to look at the indefinite integral of dx over square root of 4x squared plus 1. 4x squared plus 1 can be rewritten as 2x quantity squared plus 1 squared. Now be careful from the first slide when you set this up. Because it's addition, we are going to use tangent. But remember, it was x equals a tangent theta. Well, this time our x is 2x. So 2x equals 1 tangent theta. Another way to write that would be x equals half tangent theta. Taking the derivative, dx is equal to 1/2 secant squared theta d theta. Now, why did I take the derivative? Because I've got to find a replacement for dx in the original problem, and I've got to make a substitution for this radical term. Dx is equal to 1/2 secant squared theta d theta. This radical term, 4x squared plus 1, underneath a square root, in red, I copied that down. Recall that our substitution started with 2x equals tangent theta. If I square both sides, 4x squared can be replaced with tangent squared plus 1. Using your Pythagorean identities, tangent squared theta plus 1 can be replaced with secant squared theta, and the square root of that is just secant theta. That's where I made this substitution in the denominator. Up top, the 1/2 secant squared theta d theta, that all was the replacement for dx. This radical in the bottom simplified to secant theta. Now cancel you a secant from top and bottom, and you're left with 1/2 times the integral of secant theta d theta. The integral or antiderivative of secant theta we looked at in a previous section, and it has, and you can also again look these up on your Google Drive folder for the class. This antiderivative is natural log of secant theta plus tangent theta. So we've got our antiderivative here. Don't forget to multiply by a half and add your constant of integration. Because this is an indefinite integral, we have to go back from theta back to our original variable x. Here's how we do that. 2x equals tan theta. Down here in your lower right, I've rewritten that 2x is equal to tangent theta. You can create a fraction by dividing by 1, and that will give you a right triangle. I marked theta. I always mark it in the bottom. You can pick where you mark it. Tangent is opposite over adjacent, and putting that little trick of doing over 1 gives you a second number to work with. Using Pythagorean theorem, a squared plus b squared equals c squared gives us this third side, which is the hypotenuse, and that's the square root of 2x squared, which is 4x squared, plus 1 squared, which is 1. Once you have all three sides labeled and know their lengths, then you jump back in and you can convert from theta back to x. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. Square root of 4x squared plus 1 over 1. Tangent, we already know what it is. It's 2x. So tangent theta becomes 2x. Secant theta becomes square root of 4x squared plus 1 under the radical. And that's our antiderivative. Don't forget the 1/2 out front. So we have 1/2 times a natural log. And because this term can be negative, we do absolute value. And we've replaced the thetas back with x. And also don't forget your constant of integration. Third example is a case of a definite integral. Now, from what we know about indefinite versus definite integrals, if you make a substitution, then you don't have to go back to the original variable. That's one plus side. One of the downsides is if you do switch variables, you have to be sure you correctly change your upper and lower integral limits. And so that's why I want to do this problem with you, is to show you what happens in a definite integral situation. So let's integrate from square root of 3 to 2 the square root of x squared minus 3 over x dx. Everything, in order to eliminate this radical, we've got to make the appropriate trigonometric substitution. Everything in the original integral will be swapped out in terms of theta. How do we do that? The square root of x squared minus 3 can be written as a square root of x squared minus square root of 3 squared. So the x term, the a term, secant theta, and that's because it's variable minus constant. From the first slide, if it's in that order subtracted, you use secant. If this had been 3 minus x squared, then we would use a sine theta. Excuse me. Once you've got your substitution in place, take the derivative. Derivative of x is going to be square root of 3 secant tangent, both of them with respect to theta, d theta. This x we replace with square root of 3 secant theta. This dx we replace with square root of 3 secant theta tangent theta d theta. And then the numerator, that becomes 3 secant squared theta minus 3. Let's see if we can't reduce any of this. The square root of 3 secant thetas, since it's all multiplied, those can be immediately canceled. In this radical, factor out a 3, that gives you 3 parentheses secant squared theta minus 1. Secant squared minus 1 can be swapped out with tangent squared. So this radical, using factoring and Pythagorean identity, can be rewritten as 3 tangent squared theta. Now notice this little magic trick. My 2 and square root of 3 suddenly became pi over 6 and 0. Why is that? Well, let's go to our substitution. Look at this line. Take our top integral limit, 2. When x is 2, this substitution becomes 2 equals square root of 3 secant theta. Solving for your trig function, that's 2 over square root of 3. Remember, secant is cosine flipped over, so cosine of square root of 3 over 2 is pi over 6. That's the appropriate angle. The bottom limit, square root of 3, when x is square root of 3, in your substitution becomes square root of 3 equals square root of 3 secant theta. Solving for secant theta, square root of 3 divided by square root of 3 is 1. The reciprocal of 1 is still 1, so what angle has a cosine value of 1? That's 0 radians, and that's why the bottom limit becomes a 0. You have to filter the upper and lower limits when they're in terms of x through your substitution to get the new variable's value. Now we're set. Square root of 3 tangent squared theta can be written as square root of 3 tangent theta times this tangent theta, and I forgot to put a theta on it. Let me write that in. There it is. Okay, so let me go back, and square root of 3 pulls out front. That becomes tan theta times this tan theta is tan squared theta. D theta drops down. Since tangent squared can be written as secant squared minus 1, that makes it easier to find the antiderivatives. The derivative of tangent is secant squared. The derivative of theta is 1, so that makes sense that these are our antiderivatives. Now, because this is a definite integral, we're going to evaluate the antiderivative at pi over 6, subtract, and then reevaluate at 0. Square root of 3 times tangent pi over 6 minus pi over 6 minus tangent of 0 minus 0. Well, this whole back section goes to 0. Tangent of pi over 6 is square root of 3 over 3, and you can find that value on your unit circle, minus pi over 6. Distribute square root of 3, that becomes 3 over 3, which is 1, minus pi times square root of 3 over 6. This is your exact answer. If you type this carefully into your calculator, this is an approximation to 4 decimal places. Let me remind you also that because we had a definite integral, once we transformed x's into thetas, we never had to go back to x's. Indefinite integrals are ones where you have to return back to the original variable. I hope this helps. Don't forget to check your Google Drive folder for homework help. These problems are very tedious, and you have to kind of keep your wits about you, and also be familiar with your trig identities, specifically the Pythagorean identity section, because that gets heavily used. Take your time, make your substitutions good. If you have any troubles, reach out by email or call. More than welcome to stop by during office hours, and you can also ask in class. I try to work a lot of examples in class.